Have you ever looked at the world and thought, it's all just one giant, incredibly complicated game, and we're all just trying to figure out the rules as we go? Well, if you have, you're in good company. The legendary physicist Richard Feynman saw it exactly that way. So let's dive into his view of our amazing journey to decode reality. And this is Feynman's brilliant central idea. Imagine we're just spectators, watching this cosmic chess match unfold. We can't ask the players, the gods, so to speak, what the rules are. All we can do is watch the pieces move, look for patterns, and slowly, painstakingly, try to figure out the laws of the game. And those laws? That's what we call fundamental physics.
All right, so let's wind the clock back a bit to a time when physicists really thought they were getting close to figuring it all out. They thought they had the rule book practically written. The game looked simple, it looked predictable, it looked almost solved.
So before 1920, the universe seemed to operate like a giant, beautiful clockwork machine. The chessboard was just regular old 3D space and time. The pieces were particles, like atoms. And the rules seemed pretty straightforward. Things move in a straight line unless a force pushes or pulls on them. And at the time, there were really two main forces in play. Gravity, which was this simple long-range pull, and then this messy, complicated set of short-range forces that they knew held atoms together. But then a new piece appeared on the board. And this piece wasn't just another pawn. It completely changed the game. It was the electrical force. And it turns out this is the force that really runs the show when it comes to atoms interacting. And its strength is, well, it's almost impossible to comprehend.
To really get a feel for how powerful this is, get this. Feynman did this amazing calculation. He said, imagine you take two tiny grains of sand, just a millimeter wide, and you put them about 30 meters apart. If you could somehow strip out all the electrons from both, the leftover electrical repulsion between them would be a force of 3 million tons. It's an absolutely mind-boggling amount of force, and it's why our world is so perfectly electrically neutral. So, how does this ridiculously strong force actually work? Well, it led to this revolutionary idea of a field. Think about it like this. If you have a little toy boat floating in a bathtub, you don't have to touch the boat to move it, right? You can just push the water next to it. You're creating a disturbance, a condition in the water, a field. And that is what moves the boat. And that's exactly how electric charges interact with each other across empty space.
And this concept of a field led to something Feynman called the Great Amalgamations, which is just a fancy way of saying we started unifying ideas. All of a sudden, things that seemed totally different were revealed to be the same thing. Heat wasn't some mysterious fluid. Nope, it's just the jiggling motion of atoms. And even better, electricity, magnetism, and even light itself were all just different faces of this one single thing, the electromagnetic field. The rules of the game were getting simpler and way more elegant.
And this unification is just beautiful. The only thing that separates the radio waves bringing you music, the visible light you're using to see right now, and the X-rays a doctor uses is the frequency, how fast the field is wiggling. It's all the exact same phenomenon, just at different speeds. You can see why physicists felt like they were getting really close to the end of the game.
But just as it looked like they were about to declare checkmate, the physicists discovered something stunning. They'd been misreading the board. The rules they thought they knew, they were about to be thrown right out the window.
Feynman really put it, as bluntly as possible, the world down at the tiny scale of atoms and electrons, it doesn't just behave a little differently, it behaves nothing like the world we're used to. It's a place where all of our common sense just completely breaks down. And here was the huge, glaring puzzle that classical physics had absolutely no answer for. Okay, so we have a positive nucleus and negative electrons, and opposites attract. So why don't the electrons just spiral right into the nucleus and the whole thing just fizzles out? Why are atoms stable? Why do they take up space? The old rules said they should collapse in an instant. The answer comes from a completely new and frankly completely bizarre rule of the game, the uncertainty principle. It says there's a fundamental limit to what you can know. If you wanted to trap an electron inside a tiny little nucleus, you'd have to know its position very, very precisely. But the rule says if you pin down its position that accurately, its momentum, how fast it's moving, becomes incredibly uncertain and, on average, enormous. That energy would be so huge it would immediately blow itself right out of the nucleus. The very thing that seems like it should cause collapse, attraction, is prevented by this fundamental uncertainty. Now, this wasn't just some small tweak to the rules. This changed everything. The old clockwork universe was gone. In classical physics, if you knew everything about the present, you could predict the future perfectly, deterministic. But quantum mechanics says, no way.
All you can ever know is the probability of an outcome. You can set up the exact same experiment twice, and you can get different results. Nature, at its very core, plays with dice. So, what did physicists do? They took these strange new quantum rules and they masterfully combined them with that incredibly successful theory of the electromagnetic field. And the result was a theory called quantum electrodynamics, or QED for short. And it is, without a doubt, the most successful scientific theory of all time. The success of QED is it's breathtaking. This is the theory that underpins all of chemistry, all of biology. It perfectly describes how light and matter talk to each other. It even predicted the existence of antimatter before anyone had ever seen it. As far as everything outside the atomic nucleus is concerned, QED has never, not once, made a prediction that's been shown to be wrong. It's that good. Okay, so QED is the rule book for everything outside the nucleus. But what happens when you crack that nucleus open and look inside? Well, you don't find a simple, elegant picture. Oh no. What you find is chaos. It was like discovering a whole new box of weird, unexpected chess pieces with no instruction manual. And that led to the next giant question. Think about it. A nucleus is packed with positively charged protons. They should be repelling each other with that enormous electrical force we talked about, trying to fly apart. So what in the world is holding them together? There has to be another force, a new force, that's even stronger. The search for this strong nuclear force was, well, it was a total mess. A physicist named Yukawa predicted there should be a new particle that carries this force, and then, hey, they found a particle with the right mass. But it didn't feel the strong force at all. It was the wrong piece. It was the muon. Later, they finally found the right particle, the pion, but the theory describing it was so insanely complicated that no one could actually calculate anything with it. And things just got worse from there. As they built more powerful machines to smash atoms, they just started discovering dozens and dozens of new particles. Pions, kaons, lambdas, sigmas, the list goes on and on. It wasn't the simple, elegant game they had hoped for. It was a chaotic, confusing particle zoo, and nobody knew what was going on. And that brings us, more or less, to today. Now, out of all that chaos, we've managed to piece together a new map of reality. It's not a complete map, not by a long shot, but it shows us the parts of the game we understand and, more importantly, where the frontier, the mystery, still lies. So here's our current understanding of the 4 fundamental forces that run the entire universe. We've got electromagnetism pretty much figured out, that's QED, and we've known the law for gravity for a long time, but the weak nuclear force, the one responsible for certain types of radioactive decay, we only partly understand its laws. And the strong nuclear force, the most powerful force of them all that glues the nucleus together, its fundamental law is still unknown. It's a deep, deep mystery. So if you were to draw a picture of our knowledge, it would look something like this. The vast majority of phenomena are covered by laws we know really well: gravity and electromagnetism. Then there's a chunk for the weak force, where our knowledge is kind of shaky. But that last piece of the puzzle, the strong force that governs the very heart of matter, that part of the rulebook is still pretty much a blank page. You know, Feynman said this decades ago, and it's just as true today. We're getting better. We're gradually, carefully feeling our way through the darkness and figuring out how these subatomic pieces move. But the honest truth is, we have no idea how much of the game is left to discover. And that leaves us right here with this amazing, tantalizing question. We've figured out how the rooks move and the bishops and the pawns. We understand most of the board. But as we start to explore the most extreme corners of the game, inside a black hole or at the moment of the Big Bang, what completely new, unexpected, and mind-bending rules are the gods playing by that we haven't even dreamed of yet? The game, it seems, is very far from over.